Hello and welcome everyone to another webinar series from Amsterdam Data Science. This week we have partnered with Elsevier and The Few to explore natural language processing and text mining for health research. To quickly introduce myself, I am Anita and I work with ADS. ADS is a network organization that seeks to promote and foster the data science and AI ecosystem here in Amsterdam. We do this by connecting industry, academia, and society. And some of the activities that we're involved with are webinars such as these to provide people with more knowledge and insights in the field of AI and data science. All right, so without further ado, I want to start sharing introducing our first speaker, and that's Zubair. So Zubair is a principal NLP scientist at Elsevier. He has a PhD in clinical text mining and a professional doctorate in engineering. He's been working at Elsevier for over 5 years, and his main interests are in the fields of NLP and NLU using deep learning methods. Ever since the COVID-19 pandemic broke out, the academic and scientific research community, as well as industry and governments around the world, have joined forces in an unprecedented manner to fight the threat. In this combat against the virus responsible for the pandemic, key for any advances is timely, accurate, peer-reviewed, and efficient communication of any novel research finding. Zubair will present a novel framework to address the information need for filtering efficiently the scientific bibliography for relevant literature around COVID-19. The contributions of their work are summarized in the following. They define and describe the information need that encompasses the major requirements for COVID-19 article's relevancy. They present and release an expert-curated benchmark set for the task, and they will introduce Quora, COVID relevancy algorithm, a deep active learning model to identify core scientific articles. So I'd like to I'll give the stage to Zubair to start sharing his screen and start his presentation. Thank you very much, Zubair.
Well, first of all, good afternoon, everyone. I hope everyone is doing well under these still challenging circumstances. And thank you for having us on this webinar. Today, I'll talk about our work that we did actually last year when the pandemic broke out, about identifying these core scientific articles for different researchers and clinicians and to satisfy their information need. Before that, Anita has already introduced me, so I'll probably just skip over it. I've been working in Elsevier for over 5 years. Before that, I was working at Rasmussen University Medical Center, and before that, I was working at Philips Healthcare. So very quickly, most of you already know Elsevier, but for those who still don't, as in a global information leaders, we help researchers in making new discoveries and having more impact on the societies. We help clinicians to treat their patients better and save more lives. And we also help nurses in their education to get better jobs and eventually to save more lives. We have a history of collaboration with you and the EDS. So currently our ongoing continuous internship program. This year alone, we had about 200 speed dates in the thesis fair. And there are currently 11 students working on their internship/master thesis from UIDS on different data science related projects, related to classification, NERs, automating the machine learning processes, summarization, trend prediction, knowledge graph. This should give you an idea of the kind of projects, the kind of things that we do internally as well in the company. There's a great chance that few of these interns will get a return offer and become a full-time employee with us. We also started the Elsevier Discovery Lab last year as part of the Innovation Center for Artificial Intelligence. It's co-funded by University of Amsterdam, Vrije University, and Elsevier. Currently, we have 5 PhD postdocs, 3 researchers, and supporting staff. And they work on topics that are of mutual interest, such as knowledge graphs, question answering, and recommended systems. This was very briefly how we are collaborating. If you want to know more, please reach out to us or look at our website. Now, on to the actual topic today. I'm going to talk about our deep active learning algorithm to identify the core articles. As Anita mentioned in the intro, that ever since the pandemic broke out, everyone, the government agencies, researchers, they all started working together to fight the pandemic, to understand the disease better, to understand the spread, to find the cure, to find the vaccination, and all. So they all started working together. And in this combat, one of the key advancement is the key for actually advancement is having access to the accurate, peer-reviewed, and novel research findings. For this reason, almost all scientific publishers, they open up their digital libraries for people who are interested, all the researchers, clinicians, and whoever was interested. As you can imagine, once you have all these data sources available, it becomes a little challenging to find the relevant documents for your information need. Here's a quick example. This article is talking about the virtual interviews in the era of COVID-19. It has all the keywords to say that, okay, this is about COVID-19, but if you look into it, it's not talking about the disease itself. It's talking about the impact of disease. So such an article would be of less interest to the clinicians who want to understand the disease, understand or trying to find the cure for the COVID-19. And then, yeah, there are plenty of such cases when you start looking for COVID-19 material. So last year, when we started our work, our main goal was to ensure that the novel findings that are made available to the scientific community as quickly as possible. And we did this in two ways. We implement our acceleration initiative in the editorial process, which is commonly known as the peer review process, and the production processes. And we also implement monitoring systems to make sure that the important articles, they are not stuck somewhere in the process. The work that I'm presenting today is part of the acceleration initiative. The goal was to identify the primary COVID articles as quickly as possible, so we can share it with the community. I'll come back to what I mean by a primary COVID article, because that is a key concept in our work. So when we started last year, of course, we didn't have any training set, to identify, because it was such a new thing. So naturally, we started off with a simple keywords query, keyword classification. Our subject matter experts, they came up with this query that you see on your screen now, about 8 keywords. And then we ran it through our system, and whatever we found on ScienceDirect, we made all available for free on our novel Coronavirus Information Center webpage. We also contribute to Code19. A few of you might know it's one of the largest open research data set on the COVID-19, and the source, they draw the content from WHO, PubMed, PubMed Central, bioRxiv, medRxiv, and few other sources. So we do contribute to that as well. So apart from the WHO, who actually do hand curation of the relevant content, all other sources, they use the same query that we started to find their content. You can see the query as well here, and the Code19 paper is available for you if you want to know more about the sources and the statistics of different publishers and some other interesting detail. I think you should explore that. But we soon realized that the initial query was too limiting. So, and of course, the new content was coming. We started observing new patterns, new keywords. So naturally, our subject matter experts, they analyzed the content further, and they came up with few additional terms. So we expanded our query from 8 words to what you see below, actually, quite few additional terms in the query. And of course, I mean, keyword-based solution. The advantage is that you don't need any training set, right? So, and typically the recall is high. So if you have all the generic keywords in there, your recall would be high. But the downside is that your precision would be low. So there will be many false positives, like the one I showed earlier about virtual interviews. And secondly, you need domain expertise to actually come up with the terms for whatever system you're building through your keyword based classification. So naturally, we wanted to move away from the keyword based solution to more machine learning based solution. But there are a few challenges when you want to implement such an approach. The first one being there is no gold set, there is no training set available, so you need to create one. And then there was no definition of what is relevant actually for different different stakeholders, for researchers, for clinicians. What exactly are they're looking for when they're trying to find interesting articles? And when you are to create a goal set, you need to hire subject matter experts. It's time consuming and costly. And sometimes when you do a random sample for your goal set, sometimes it leads to some suboptimal solution. So the first thing that we did, we interviewed many people, many clinicians, researchers, data scientists, doctors even, to understand their information need. And we summarized all the information needs into this inclusion and exclusion criteria. So primarily, well, we have two classification. We have the primary impact articles that talk about the diagnosis, treatment, vaccine development, pathology, virology, the population-related phenomena, how the hospitals are dealing with the pandemic, all your propagation modeling, and things like that. We all classify it as primary impact articles. These are the articles that all the clinician, researchers, data scientists, they are looking for. And then we have the secondary impact articles, articles talking about the impact of COVID-19 on economy, education, transport, social media, and there are many others coming these days now. The example I showed, the virtual interviews will fall under the secondary impact article. So our goal was to actually identify the primary impact articles and filter out the secondary impact articles in our work. Now, once we have this relevancy definition sorted, of course, the next step was to create a training set, a goal set for to do any machine learning work. Now, your typical way of building a goal set is first you draw a sample from your population, and then you ask your subject matter experts to actually go over the whole set, do the labeling, and once you have the label set, then you start developing your machine learning methods. First of all, this is time consuming, and often the quality of the goal set, training set will depend also on how you actually sample the data from your population. Now, there is also another way to do that, which is the active learning, which we use. So in active learning, what happens is, so first we start off with the base classifier. I'll come back to that. So what happens is that we use an acquisition function and we select an example from the set of examples that we have fed into the active learning, and we ask the algorithm, okay, tell us what we should label next. So there are many different ways to get that sample. There is uncertainty sampling, there's a boosting, there are many other ways how you can actually implement that acquisition function. So once your acquisition function has actually identified a document to annotate, then you ask your human experts to actually label that. What they do is they verify if the classification done on that drawn sample is correct or not. I will show it to you. Once we have that label set, we add it back to our training example, the small training set that we started off with. And then we retrain the model again. So this continues until you either exhausted all your samples that you started off with, or you have reached a plateau that you see that, okay, now we are actually reached a place where the algorithm is not learning much. So it's probably a good time to stop. So here you see on the left is the screen that was presented to the subject matter expert. So the acquisition function identified, okay, this is the document I should we should label next. And then on top, you see that prediction is already given by the classifier. And on the bottom, the tick mark and the cross mark, it's actually asking the subject matter expert to validate whether the classifier is correct or incorrect. Now, this is very interesting because we use the uncertainty sampling. So that means the algorithm will pick a sample where it's actually most uncertain about whether this should be a relevant covered or corona article or not. And then if, for example, this is a false positive, and then the SME will click on the cross mark, the algorithm will learn from it, or even the same way when it's marked as correct, it will learn from its mistakes and its correct classifications. So we started off with 20,000 data samples that we feed it into the active learning, and we only needed to do about 9,000 before we reached that threshold where we were satisfied with the quality of the classification, and sort of reached that plateau where we knew that now it will become very hard to improve further. So as for the actual classifier, we use BioBERT. BioBERT, is a variation of the BERT, only that it's pre-trained on biomedical domain corpora from PubMed abstracts and PMC articles. It's already pre-trained, but then we fine-tuned it using the active learning approach, which is actually not common at all this way. So our algorithm, CORA, which we call it, Covert Relevancy Algorithm, has two components inside. We still use the keyword-based query, the classifier, to get to identify all potential articles, because again, the recall of such a query is extremely high. And then we use our machine learning classifier to filter out the secondary impact articles. So we only are left with the primary impact articles after we do the classification, after it's passed through the CORA. Here is a quick example of how the training flowchart look like. So what you do first you create a very small seed, train, and dev set, and you also create a small test set, and then you fine-tune a model on that seed data. We call it weak-based classifier, because again, you don't need thousands of samples for this one. Just 100 or so would be enough, depending on how complex the task actually is. So once you have the seed data, you evaluate. You establish your baseline. Okay, this is the performance of my base classifier, and then you enter into the active learning loop, which is which I explained earlier. So what happens is, so the acquisition function draws a new sample. We use the uncertainty sampling, as I mentioned before. So it continues until, we have the data or the threshold is below what we have specified. So we keep on fine-tuning the model. Once we have exhausted either all the data or we have reached that plateau, then we come out of the active learning, and then you evaluate on the test set and to get our final classifier. Here I'm showing you the evaluation on the BioBERT and the keyword-based approach. As you can see that the precision and recall, especially of the keyword-based approach, is very high, 98%. For our BioBERT, it's about 91%. But overall, F-score is better than the keyword-based classification. And our test set was about 1,234 articles, which were manually created by the subject matter expert for independent evaluation. Now, when we first released our version, the CORA version, on 11th May, we had these, we set this threshold. So if the classification, the probability was above 0.7, we were fairly confident that this is a relevant article. And if it was below 0.4, it was not relevant at all. But then we had this gray area from 0.4 to 0.7, where it was all the boundary cases were actually there. So our goal was to actually reduce that stage. So we keep on improving. We keep on working on the active learning. We learn more, and then we managed to reduce that gap from 0.4 to 0.7. and we come down to between 0.45 to 0.5. And by the 30th June, we actually closed that gap almost completely. We still had a few cases on the borderline, but overall, our classification was sort of reached its plateau by 30th June. So we kept on improving using the active learning. I'm going to show you a few examples of where, for example, the Quora finds those second impact article and classified them as false positive. So here it's talking about the geographical distance to the epicenter of COVID-19, right? So it doesn't talk about the disease itself. So the algorithm successfully classified it as a secondary impact article rather than the primary one. Similar cases here. Talking about the COVID-19 social distancing in the Kingdom of Saudi Arabia. Again, doesn't talk about the pandemic, doesn't talk about the disease, but mostly about the impact of it. And then we have another example. There are a few medical keywords in there, but still the algorithm was intelligent enough to understand that, okay, this is not the right article that would be classified under the primary impact articles. Right. So as you know that when you have your machine learning models deployed in production, model drift, right? So there are two types of drift. There's a model drift, and then there's a data drift. And we often monitor this drift after every so months to understand if the algorithm still is working as it was supposed to. So after 6 months, we did a drift test. So we actually ran that query, the initial query, and we selected about 1,845 documents that were classified against that base query that we initially used. So the precision of the keyword approach dropped hugely to 0.36. And our Quora, the algorithm, precision was 0.80, recall 96, and F1 of 87. And now to just put things in perspective, when we started, the precision of the keyword approach was 0.74. As you can see that in 6 months' time, for the keyword-based approach is really fall behind, because again, the new content was coming, the language was changing, the new concepts were appearing, which were not appearing in the initial query, and then there are more articles which were actually false positive in the set. For precision of our initial Quora model was 0.89. We see a small drop in there as well from 0.89 to 0.80, but overall it was still much better than if it had continued with the keyword-based approach. And that's where you would see the advantage of using a language model for such classification. Right. To summarize, we presented our novel solution in EMNLP end of last year in December. Our main contribution was to actually create that framework, right, of inclusion and exclusion criteria to actually summarize all the information need of different people. Then we created that simple but very effective deep active learning approach. And then we compiled this benchmark set. Actually, the training set that we compiled is available on Mendeley data, so anyone can actually download and start experiment, and you can use the same framework to actually classify your own content in your own way. We also demonstrated that the algorithm can achieve 96% F1 score in detecting non-relevant documents. This is very important because that is all the noise that you would find if you don't use a machine learning classifier but just use a simple query. And the 91% detection of the relevant document. That means the recall. There are still few documents that were missing, but overall the both precision and recall was very high. As I mentioned earlier, we did publish. There's a lot more detail than what I just mentioned in the article, so I encourage you to go through it. There are links to the data set as well in the article, so you can find that and start working off it. I think that's about my time. So I would like to thank you all for listening. And yeah, if there are any questions, I'm happy to take it.
All right, thank you very much for that, Zubair. That was a very informative presentation. In the interest of time, I think we've got about 3 minutes left, so probably might only have time for this one question that was already put forth, and this is a question from Gino. So they would like to know, how do you know that you've reached a plateau? Oh, wait, hang on. How do you know that you've reached a plateau in the absence of a gold standard data set? Since your labeled data is selected in a biased way, I assume you can't just look at the test set accuracy.
Right. Yeah, a very good question. So what happens is when you use the active learning, it also depends on what tool you're using for your active learning. We use Prodigy. So what happens when you use Prodigy is that, as I mentioned earlier, remember, it gives you an article to label, and then it doesn't ask you to provide the label for the article. It asks you to validate the classification that it has already done. So if you have done the, if you say, okay, the classification is right, that will go as a true positive, otherwise it will go as a false positive. So you'd see that precision curve in the tool itself when you start doing these active learning validation. So what happens is, initially you would see that your precision will actually go more linearly, that you see the algorithms learning very quickly. But there will come a point when you would see that it started to straighten out. That's where you know that, okay, now it's actually taking much more articles to find the true positives by the article, or the other way around. Or actually, there are very few cases where you would now disagree with the classification done by your base classifier because it has already learned too much. So that's where you would see that, okay, I'm now reaching a place where most of the classification done, most of the examples that are shown to me by the algorithm, they're already correctly classified. So that's where you know that you hit that plateau, and then you can stop. Because after that, it would take much more effort to gain just a tiny bit. I hope that answered the question.
All right, thank you very much for answering that. I'll just take one more question, so this will be the last one. So the question is, did the use of BioBERT outperform classical bag of words or topic modeling?
Yeah, so we did experimented with different models, non-language models as well. Performance was a little bit low of those models, but one main reason of using the language model was what I shown you in the last few slides about the drift. We knew that it was such a new field, and there are new articles coming with potentially new type of language, new type of concepts coming. So we wanted to actually, so that was our intentional decision to use a language model, because we knew that the language would be changed and the language model would be much more suitable to handle the variations that we would see in the future, comparing to your traditional machine learning algorithms.
All right, thank you. So there are a couple more questions, Zubair. So if you won't mind answering some of those in the Q&A functionality, that would be great. But I'll now move on. So thank you very much for that. I'll move on to our second speaker, who is Stan. So I'll just introduce him. So Stan has a background in linguistics, but made the switch to artificial intelligence and NLP during his master's studying text mining. He wrote his thesis about the use of text mining techniques to classify medical patient notes. So to kind of introduce the topic that he'll be speaking on, falls that happen in hospitals pose a serious clinical and legal problems with regulatory consequences. To effectively use fall prevention techniques, hospitals need to have information about the falls, like location and time. But since falls are often unreported or misclassified in incident reporting systems, the best source of information are medical patient notes. Reading all these notes manually is very time consuming, so text mining techniques can be applied instead. Stan will be presenting their design for a system architecture, discussing primarily its implementation and results at the AUMC hospitals in Amsterdam, while also reflecting on challenges that we will have to overcome in the continuation of the project. So without further ado, I'd like to give the stage to Stan so he can share his screen and start presenting. Thank you very much, Stan.
So good afternoon, everyone. I'm going to present my master's thesis I wrote last year about the use of text mining techniques to detect fall events in medical patient notes. During this time, José Morante was my supervisor from the university, and Edwin Gelijn was the supervisor from the hospital. And they are both here today as well to add any comments when needed or to answer any questions you may have at the end of this presentation. So this fall prevention project has been going on for much longer than my thesis, and both Rosa and Edwin have been working on it since the beginning. so they might know more about the specifics and the details of the earlier stages of the project. These are roughly the topics that I will talk about today, but I'll try to pay specific interest in the data-related and the machine learning parts. So, why did we do this research? Well, first of all, out of all the adverse events that happen within hospitals, falls and mismedication are the most common. Around 30% of the falls that happen in hospitals will result in injury, out of which 4 to 6% are major injuries, including things like fractures, excessive bleeding, and sometimes even death. So next to that, falls also can have major emotional effects, like causing a fear of falling again or leaving family members with a similar fear. And then finally, falling in the hospital sometimes lengthens the hospital stay, which means the hospital bed is occupied longer, which in turn results in additional healthcare costs. So then, why is this still a problem? Why didn't we solve this, and why haven't we found a way to prevent people from falling? The problem is, we don't exactly know which people fall and why they fall, or when they fall, etc. So in order to create an effective fall prevention program, hospitals rely on good measurements of adverse events. But often this information isn't readily available, since falls are difficult to measure reliably, and they tend to be unreported or misclassified in incident reporting systems. Fortunately, however, research has shown that medical record reviews can increase the proportion of events captured. But since the hospital can have millions of medical records, manually reading them would be very time-consuming, especially since nurses would be the ones reading the notes, and this would take away valuable clinicians' time. And this is where data scientists come into play. The use of natural language processing techniques shows promising results in aiding to construct a better picture of the fall events that happen in hospitals. And these are a few papers about adverse event detection architectures, and I will explain 2 of them in the next section, the related work. So firstly, one of the oldest papers I could find about this topic was by Melton and Ripsack in 2005. And they used NLP to identify whether text in discharge summaries contained at least one of the 45 event types that were chosen from the NIBORDS, which is a mandatory adverse event detection system in the United States. They used a rule-based model combined with simple keyword matching, which consisted of a lexicon with hand-chosen predictive words in combination with metadata like the day of birth and the department of the hospital the patients were in. And their system matched the performance of human experts, which was about 28% recall and 45% precision. Where was I? I will do one more related work. So the previous one was from 2005, which didn't use any machine learning techniques. And this paper is from 2017 by Wang and others. And it talks about an SVM they constructed to detect adverse events in incident reports. And they reported the performance of the model on several subsets of adverse events, including falls. And the input of their model was a combination of distributional characteristics of text, like the binary count of words, the term frequency, and the so-called TF-IDF, which is the term frequency inverse document frequency. And this is a metric that is used to evaluate how relevant the word is in a document given the whole set of documents. And it does this by increasing proportionally to the number of times a word appears in a document, and then offset this by the number of documents that contain the word. And their model reached a 91.3% recall and an 86.5% precision. And this may seem like a lot more than the previous work, but you should keep in mind that this performance is evaluated on the detection of just one subset or category of adverse events, namely false, whereas the previous work was about detection of nodes that contained at least one of 45 event types. And also this data for the research was a set of incident reports, and those are specifically written to report an incident, meaning the task was quite different from the last one. And now about the data that we used. So in our project, we used the data set that consisted of medical patient notes from the AMC and VUMC hospitals in the year 2017 and 2018. And in total, we had over 14,000 notes consisting of over 260,000 sentences together. And in this figure, you can see the distribution of the amount of sentences per note. And it shows that most notes contain few sentences and only a few notes contain many sentences. And not only the length of the notes varied, also the length of the sentences was variable to a great extent. So this picture shows the distribution of words per sentence. And yes, this graph does reach all the way to 800, you see on the right, but the frequency is too small to show it. I think there were about 260 sentences with more than 300 words. So now, why am I showing you this? Well, in my opinion, I think it perfectly shows one of the main challenges in text mining. In text mining, one tries to extract information from a textual data source, which is intrinsically unstructured data with great variation. And especially in this case, since the cause for these extremely long sentences to appear in the dataset is quite easy, some nurses and doctors didn't use punctuation mark, including full stops in their notes. So the task we had to solve in this project was one of modeling a classifier to classify notes on whether they contain the description of a fall incident or not. And since the data for this project contained personal information, the only way to access the data was in a protected environment, a remote desktop within the hospital server. And this meant that the choice of the model was limited by the computational capabilities of the server. As a result, we chose the same model Wang and the others used, an SVM, instead of a computationally more complex model like a neural network. And since it was a supervised classification task, we also needed training data. And in natural language processing, training data often is a set of annotated text. This means that nurses had to read medical notes and mark the parts that contain the fall description. And there is a catch. Even though falls are a serious problem, they are relatively infrequent. And to gather a set of, for example, 1,000 falls, one would need to read hundreds of thousands of notes to find them. And that would obviously take way too long. So the people who worked on this annotation process before my thesis even started found a clever way of solving this. They constructed a set of rules to pre-select the notes in an attempt to filter out a big portion of the non-fall containing notes. And I wanted to mention this because even though this is a clever solution, it does have an effect on the rest of the project. The annotated dataset was the source for both the training set, but also for the validation and the test set. So if this set of rules were to delete a specific type of fall mention, these mentions would, 1, not be part of the training set, and thus the model wouldn't be able to find them, and 2, since they also wouldn't be part of the validation set, the evaluation phase wouldn't see this as a mistake. And consequently, this can make it very challenging to convert the project from its academic setting to the more practical environment and judge its performance. So when the annotators found a fall in a note, they could choose out of 3 categories to mark them with: an in-hospital fall, an out-hospital fall, or a fall that happened in an unspecified location. And this is exactly what the annotators did. In total, they read over 12,000 medical patient notes, out of which almost 7,000 notes were found to contain a description of a fall event. And almost 1,500 of them were in-hospital falls, 5,000 of them were out-hospital, and a few were unspecified. And since the hospital was only interested in the notes that they were sure of that they contained in-hospital fall descriptions, for the purpose of this project, the falls in the unspecified locations are regarded as out-hospital falls as well. And that leaves us with the following data set. I was given the task to construct a model that was able to accurately categorize the notes that contained an in-hospital fall. And in this diagram, you can see that the annotated data set is a subset of all medical notes, and all falls are a subset of this annotated data set. And the classifier had to be able to classify the notes within the top right square, the in-hospital dataset. And originally, after the classifier did its magic, a human reader would take a look at the resulting selection and then further filter out any mistakes made. And for this reason, it was especially important for the model to have a high recall. So it needed to find most of the in-hospital falls, regardless of any notes that were mistakenly classified as such. And the precision score didn't really matter that much. So now that we have carefully selected an annotated dataset to work with, the question is, how do we represent this data in a computer understandable way? As I said before, language use is quite variable and textual data is unstructured. Also, text contains a lot of noise. Words or sentence constructions can be ambiguous, and often domain-specific knowledge or the concept of mutual or common knowledge affects the meaning of a sentence. So there are actually 2 parts to making the text understandable to computers. First, there is the pre-processing. This includes the process of removing parts of text that convey little to no meaning, and often NLP scientists also use available parsers and tools to reduce a sentence to more generalizable pieces. For example, one could use a part of speech tagger to find for each word in a sentence the grammatical category the word belongs to, like a noun or a verb. And as you can imagine, adding this information to the input of a model can help it make better predictions. Unfortunately, these parsers and tools are often lacking in a language like Dutch, especially considering the language used in these patient notes can be inconsistent, full of abbreviations, or just lists of seemingly random words. And since the performance of most parsers in Dutch isn't really high, chances are that using these introduces more noise to the data than it takes away, and this is why we decided not to use any parsers or tools. And other pre-processing techniques text miners sometimes use includes removal of capitalized letters, the removal of so-called stop words, which are function words that rarely convey any meaning. So for example, but, if, and, or because. And in this case, it was questionable whether this would really improve our model. Nurses and doctors already left out many of these stop words and often didn't bother with capitalizing letters. So you could imagine that if suddenly one of these characters appeared, they could have actually some meaning. And to test it, I experimented with my model both on pre-processed data and on pre-processed data. Another pre-processing step that is often used is stemming of the words, which basically means any grammatical inflections of the word will be removed. As a result, the word am, are, and being would all be reduced to the single stemmed word be. I also introduced this pre-processing step in my experimentation, which we will see in the slides about the results. And then there is the question of the representation of the words itself. Of course, a computer can't handle textual data, and we need to convert it to something it can understand, numbers. And previously, this was done by making a list of all unique words in a data set and then assigning a position in a vector to them. And then for each sentence, you could take all the words in it and put a 1 in the position in the vector that represented this word and a 0 on all other locations. And this works, but the resulting vector is extremely sparse, and only a few items in the vector would be a 1, while thousands would be a 0. Another way of representing textual data is by using the so-called word embeddings. A word embedding is a vector representation of a word based on the words that appear in its immediate context. And they are a very nifty way of embedding the actual meaning of a word instead of the word itself. And I won't go too much into depth about how these embeddings work and how they are generated, but I hope that I can show you how powerful this quite simple representation really is. So take, for example, the word cat. If you would take 1,000 sentences from the internet that contain the word cat, and you take 1,000 sentences that contain the word dog, and then you take a look at all the words that appear in its immediate distance of, for example, 3 words within from these animals, and then you can expect similar words to appear. Words like house, petting, animal, etc. And these words, these context words of cat and dog are expected to be more similar to each other than, for example, to the words in the immediate context of the word like car, even though car is just one character different from cat. So now that we've got a representation of a word that is understandable by computers, we want to get a representation of the whole sentence. And in our project, we did this by taking a weighted average of all these word embeddings to get the sentence representation. And the combination of these pre-processing techniques and then the use of these sentence embeddings resulted in a computer understandable text representation, which we then used as an input for these SVM models. There's just one more problem that we needed to tackle before we could start with the construction of the system architecture, and that is the well-known task of class imbalance. And I think we all already know a lot about class imbalances, so I will just do this quickly. As I had shown before, in total 12,000 notes were annotated, out of which only 1,500 were in-hospital false. But since the model has to classify the sentences and not the notes, this imbalance is even bigger, because even in the notes that contain a fall event, there are many sentences that do not contain a description of a fall. And to gain insight into this effect of the imbalance, I decided to also experiment a little bit with different ways of rebalancing the data. And I used combinations of undersampling and oversampling and plotted these results, all based on a paper called SMOTE, Synthetic Minority Oversampling Technique by Chawla and others. Explaining these results of the experiments would probably take another 20 minutes, so I decided to leave them out of this presentation. If you want to read about them, however, my thesis should be accessible through the thesis repository of the VU, and I will also link it at the end of this presentation. So there are basically two parts to this project. First, we want to know which sentences contain a description of a fall incident. And secondly, we want to, given this sentence of a fall, we'd like to know whether this was an in-hospital or an out-hospital fall. And we decided to split the task into these two steps, because we hoped an SVM would have an easier task filtering out the non-falls first and then distinguishing between the in and out hospitals, than it would be to filter out the in-hospital falls from both the out-hospital falls and the non-falls altogether. And as you can see in this diagram, these the top two SVMs represent this pipeline of these models. And as I explained before, the hospital especially required high recall scores, since a human reader were to reevaluate the outcome of the model. And to aid in that task, we decided to propose a secondary set of SVMs that were precision optimized. Any node that would be tagged as an in-hospital fall by both the recall and the precision optimized model would be less likely to be a mistake and would thus not have to be reevaluated by the reader. In a sense, this precision optimized SVM would add a level of certainty to the predictions. And you can see this part at the bottom half of the diagram. And then on the right-hand side, you can see the human reader. So now I will quickly go over some of the results of the thesis. First, I will show you the results of this experimentation with the pre-processing steps, and then the final performance of the model, including an error analysis. So this graph represents the recall scores in blue and the precision scores in orange. Each bar represents an experiment with different pre-processing steps on the no-fall versus fall SVM. So it was the top left SVM. And as you can see, none of these pre-processing steps really seem to influence the scores of the SVM. The recall is around 91% and the precision around 31 to 34%. And in this graph, no stop means the pre-processing step of stopwatch removal, lower means the removal of capitalized letter, and lower stop is a combination of those. And stemmed, yeah, that means just that. It's a STEM data set, where all prep is a combination of all these steps together. And then the final two bars, they say retrained. And in these experiments, I also retrained the word embedding model on a data set without all stopwords instead of with the stopwords in it. And this is a similar plot, but this one is for the in-hospital versus the out-hospital SVM. And this also shows that pre-processing steps have little to no effect on the performance of the model. So now here are the final results of the architecture. Some things to note is that the fall versus no fall SVM seems to be more extreme and better at the task they are designed to perform well on, but this comes at the cost of performing bad on the other metric. As you can see, the recall optimized fall versus no fall SVM has a higher recall score than the in versus out hospital SVM, but the precision is quite low, whereas in the second case, the precision is still average. So I hope we still have some time left. Yes, a little bit. So I wanted to take a look at the errors made by the model. Two cases. This case is the predicted tag was out hospital, but it was actually supposed to be in hospital. And as you can see, A1 basically says something along the line, walked with her and collapsed. And this should have been in hospital. But if I'm honest, I wouldn't be able to pick this out when I would read it. So probably the presence of these medical terms at the beginning of the sentence give it away, but that's all. And then the next one. So this one is the other way around. These are predicted as in hospital, but they are actually out hospital falls. And especially 2A is interesting. It says she knew she was in the hospital and that she fell hard. So I get why the model predicted this as an in-hospital fall. I would probably do the same, but for some reason this was an out-hospital fall. So the hypothesis is that the context of these nodes also influences the decision made by the annotator. And this brings us to the conclusion of the project. So in my opinion, the models show quite some good performance based on the reported recall and the precision score, and keeping in mind the purpose and the use of the models, namely a human reader will go and do a final evaluation of the output of the models. This architecture is actually already able to greatly decrease the amount of time it would take the hospital to get a good indication as to which people are falling. As you can see on the slide, it reduces the time by 85 to 90% to find a little over 90% of the falls. So you lose 10% of the information, but you get a lot of time back. However, there's still so much room for improvement, which we're actually working on now. Even though my thesis project is finished, I'm still continuing on it as a freelance NLP consultant. Some of the things we're trying to improve is, first of all, the annotation quality. The first time, the annotation guidelines weren't really clear, which resulted in different styles of annotations. Also, there wasn't room for any inter-annotator agreement, which ideally would be part of the new annotation process. And then there was the question of the model, which was an SVM due to the computational limitations. But since this thesis was published, the server has been improved and new computational capabilities opened up. And I'd really like to experiment with neural networks as well. Another thing we're trying to do is to add more of this contextual information to the model. As you could see in this error analysis, some of the sentences are extremely hard to categorize when this contextual information isn't present. And we're also going to use the model in the electronic health record system soon to get primary results and see how this project works in the practical environment. And most of all, I think this shows that the use of NLP and data science for healthcare-related challenges shows great promise. I really believe that these projects are able to improve the quality of healthcare in the long run, but we just have to keep optimizing it. And this is all that I wanted to share with you today. And as promised, a link to my thesis and some contact information. If you have any questions or comments, you can send me a message. Thanks for your attention.
Thank you very much for that, Stan. That was a very informative presentation. So I think we probably have about time for 2 questions. Right, so the first question, fall in hospitals are multifactorial. Did you learn something about the specific context?
I don't exactly know what you mean by multifactorial.
Okay, so maybe Jan Taco, if you can maybe re-ask that question, that'd be great. And then I'll just move on to the second question. Yeah. So that question is, are you planning to perform a true comparative study? As now it looks as you fall short in recall now, but maybe in practice versus real humans, your performance might be better due to human errors.
Yeah, so wait, I'm not sure if I understand it correctly. So the problem with if you want to compare this with real humans is, as I said at the beginning, for a human to find fall events in these data sets, you would have to read like hundreds of thousands of notes to even find a few of them. So even if they would perform better, and I'm expecting they would, it would just not be very time efficient to do this. So I don't think this is a good idea to do, in my opinion.
All right. And another question is, are there any plans on identifying possible relationships with drugs mentioned near in the same text?
Not as of yet. So part of the adverse events that can happen are indeed mismedication, but as of now, the hospital focuses on the falls. Maybe in the future, they also want to use a classification model on mismedication or infections or whatever, but right now it's only the falls.
All right. Thank you for that. So Jan Taco came back about that, and he means multifactorial means the disease, age, location. Does that put the question into a bit more context now?
Yeah. So this is the final goal of the project. So once we got a model that is able to identify in which nodes a fall description is mentioned, then we can combine this with the metadata to try and predict which people are prone to falling and then try to prevent this in the future. So yes, this is the final goal.
All right, thank you very much for that. Okay, all right, so that would be all for today. I'd just like to say a big thank you to both our speakers, Stan and Zubair. Thank you very much for taking the time to present these very informative presentations. I'd like to say a big thank you to the audience as well. Please keep an eye out on our Meetup page for the other events that we have coming up in May and June. And yeah, that is it for today. So once again, I just want to say thank you to our speakers. That was very great. Yeah, that's it for today. Bye-bye, everyone.
Thank you. Bye-bye.
Bye.